So welcome back, students. So today we will go to the third chapter, okay, of statistical mechanics. So in the last two, I'd given a small introduction about statistical mechanics. Why do we study statistical mechanics? It's a quantum mechanics plus statistics is equal to statistical mechanics. Actually classical mechanics plus statistics also, but since quantum mechanics is the real mechanics, that's why we are writing quantum mechanics plus statistics. And then we are nothing but here we are calculating what the most probable state of the most probable properties of the system, and based on that we are doing all the things actually. Okay. Then we had studied about we have stated that classical statistics is this Maxwell Boltzmann statistics, and quantum statistics is Bose-Einstein and Fermi-Dirac statistics. Today I'll tell about what are these actually. Then I had given a small introduction on energy level and energy states. Then I had gone to macro state and micro state. I hope you have understood. If not, then we'll again discuss it in one video. Okay, so we had talk about indistributional and distinguishable things. Okay, we had seen that the total number of microstates is 2 to the power n. Okay, total number of microstate, and total number of microstate corresponding to a macrostate is this thing, factorial n by factorial r into n minus r factorial. Okay, and total number of macrostates is n plus 1. Okay. Then at the end we had derived a very important there is a postulate of equal a priori probability, that is at any time the macro state of the system is equally likely to be in any one of its microstates. Suppose this is the macro state, it can be in any one, it is likely to remain in any one. There are 3 microstates, it is likely to remain in any one of these microstates, it is likely to stay. Okay, it is likely to stay in any one of these microstates. Okay, so this is the postulate of equal a priori probability. And last but not the least, we had come to the definition of entropy of a system in the terms of thermodynamic probability, where it is thermodynamic probability is written as this omega. It is nothing but the total number of microstates is denoted as a thermodynamic probability. Okay, and so the more is the number of microstates, more is the entropy. Okay, more is the number of microstates, more is the entropy, and less is the number of microstates, less is the entropy. That is there is a difference between thermodynamic and mathematical probability. Mathematical probability is always less than 1. Okay, but thermodynamic probability is always either its minimum value is 1 and maximum value can be always greater than 1. So this is the difference. Okay, so minimum value of entropy will be what? Ln omega, kb into ln omega. Omega minimum value is 1. Okay, so for this case, the entropy of this microstates will be what? Kb into ln 3. But for this one, this is kb into ln 1. So entropy is 0. Okay, and nature always want to stay in the state of the most probable state. Okay, nature always likes to stay in the most probable state. Most probable state is where the number of microstates are more. That is, so you see here the number of microstates here is totally 2. So most probable probability is 1 by 2. Okay, so so here these are the things. So now today we'll shift to the next topic. Okay, that is called as the phase space. Phase space. Okay. So what is a phase space? In statistical mechanics, or even in quantum mechanics also, phase space is a very very important term, okay, describing the particles. Okay, now what is this? Okay, now say in classical mechanics, okay, in classical mechanics, the position of a point particle, classical mechanics, the position of a point particle is in three dimensional space is given as what, x, y, z, and its state of motion is given as what, and its state of motion is given as px, py, and pz. Sorry, no. In state of motion is given as vx, vy, and vz, velocity. Okay, now here is an interesting thing, that for various purposes it is more convenient to denote the state of motion. It is more convenient to denote the state of motion by the momentum px, py, pz. Why? It is more convenient to denote the state of motion by px, py, pz. But the why? What is the reason behind this? The reason is that now again we are telling for classical mechanics. Okay. Now say for quantum mechanics, what happens? As I said, quantum mechanics is for microscopic particles. Now there the velocity of the particles is what? Velocity of the particles is comparable to that of light. So it's extremely high velocity, and that relativistic particle. So for those kinds of particles, the mass of the particle changes with velocity, right? In this case, for classical mechanics, mass remains constant, but for quantum mechanics, the mass of the particle changes with the velocity. So you must take into consideration the mass also. That is why we do that. It is more convenient to denote the state of motion by px, py, and pz. Okay. So to describe both the position and the state of motion, of the particle, it is required to set up a six-dimensional space. Okay, six-dimensional space consisting of what? X, y, z, px, py, pz, which is called as the phase space. Six-dimensional space consisting of x, y, z, and px, py, pz, which is called as the phase space. Okay. Which is called as the phase space. The phase space is a six-dimensional space. Okay, phase space is a six-dimensional space. Now, suppose there are n particle system. For an n particle system, what is the dimension then? Then that will be 6 n-dimensional space. Okay, 6 n-dimensional space is a 6 n-dimensional space. Okay, that is sometimes called as the gamma space like this. Okay. Now suppose how is the phase space denoted? Now suppose here that is although a 6-dimensional space. Now suppose to make it simpler, you draw a 2-dimensional space like this. Okay, you divide it into like this. You divide it into cells. These are what? These are all this cell. Okay. Okay, these are cells. Now uh, these cells are the what? The smallest. This is what? This is the. These are all of these. These are the smallest or unit cell. Unit cell of the phase space. Unit cell of the phase space. They are the unit cell of the phase space. Okay, unit cell of the phase space. Now what will be the volume of this? What will be the volume of this unit cell? The volume of this unit cell will be what? You tell me. It's very easy. It will be delta x into delta y into delta z into delta px into delta py into delta pz. Okay, definitely. These are the points. These are the coordinates of the particle in a phase space. So what will be the smallest volume of the phase space? How will the smallest volume be denoted? Delta x into delta y into delta z. So that is you are writing it as say dv. So how I can write that? Delta x into delta px, delta y into delta py, delta z into delta pz. Okay. Now what is delta x into delta px? Delta x into delta px is h, Planck's constant. Delta y delta py is h, Planck's constant. Delta z delta pz is h, Planck's constant. So that is h cube. Okay. That is h cube. So the smallest volume. Okay. The smallest volume of a unit cell of a phase space is h cube. That is, there is the difference between classical mechanics and quantum mechanics. That is, in classical mechanics, you can gradually you can decrease you can decrease the volume of the phase space or phase cell to nearly zero. But in quantum mechanics, you cannot decrease the volume. You cannot further decrease the volume of this phase cell. I cannot draw another line like this. Its volume has to be h cube. If the volume of the phase cell is equal to volume of a phase space cell. Okay. So this is the smallest volume of the phase space, then h cube. So it cannot be, less than h cube. The volume of the phase cell cannot be less than h cube. That is quantum mechanics. In classical mechanics, that is this thing. You cannot make it lesser than this. All are of equal size, h cube. All these phase cells, these smallest squares, are all are of h cube volume. Okay. Acha. So now we will find a quantity, okay, called as the density of states. So density of states, okay, density of states, DOS, or very simply the number of phase cells in the phase space, number of phase cells in the phase space, the number of phase cells in the phase space. So how will you write that? Number of phase cells in the phase space. This you will write that total volume of the phase space, okay, total volume of the phase space divided by uh, volume of this phase space cell, volume of a phase space cell or phase cell, just total volume of the phase space divided by phase cell. That is, if you calculate the total volume of these divided by volume of a single cell, you will get the total number of phase cells in the phase space. Okay, so what will be that? That will be volume of a phase cell is very easy. In the denominator, h cube will come. Okay, and total volume of the phase space will be what? Total volume of the phase space will be this integration of dv you will get. So this will be actually 6 integration 1 2 3 4 5 6 dx dy dz dpx dpy dpz. Okay, now how you can write this? You can write it like this. You can write it like this, that integration of dx dy dz into integration of dpx dpy into dpz by h cube. This is the this is you can tell this one is in the position space. Okay, this is the position space and this one is the momentum space. This one is the momentum space. Okay, now this is what? This is very easy. Integration of dx dy dz will be what? V, total volume V, okay, divided by h cube, and this will be what? this will be what? This will be actually the volume of the phase space. This will be volume of a spherical shell, volume of a spherical shell, okay, of radius p and thickness dp. Volume of a spherical shell of radius p and thickness dp. That is what? If this is shell, okay, this is p, okay, this is dp, this is dp. So volume of this spherical shell you have to calculate. This we have to do. So what will be that? That will be 4 pi p square dp. Volume of this spherical shell you have to calculate 4 pi p square dp. Okay, so now we'll do this. So this you denote as gp dp. Okay, this you denote as gp dt. Okay. Now here, so gp dp will be what? gp dp will be what? Here it will be v by h cube 4 pi p square dp. Okay. Now, if you want to calculate the the GED, okay, if you GPDP is what? GPDP is number of phase cells in the phase space in the momentum space. Okay, in between the momentum range P and P plus dP. This is GPDP. Okay, what is GPDP? GPDP is equal to the total number of phase cells. This is also called the total number of microstates. Phase cells is also called as the total number of microstates. Okay, here also I can write that number of phase cells, that is the total number of the total number of phase cells, that is microstates, the total number of microstates. Here also the total number of microstates in the in the total number of microstates in the momentum range P and P plus dP. Okay, the total number of phase cell, that is microstates in the momentum range P and P plus dP. This is this. Now if you want to convert it to GED, so GEDE. Okay, so how will you do that? V by h cube will be the same, 4 pi will also be the same. Acha, p square, what will be p square? P square will be 2m. Okay, and what will be dp? So you know that p square is equal to 2me. So if you differentiate it, what will you get? 2p dp is equal to 2m into de. So 2 will cancel. So dp will be equal to m by p. P will be square root of 2m into square root of e into de. So 1 by root 2 into square root of m into e to the power of minus half into d. So if you do it here, 4 pi, here there will be dp here. So 4 pi v by h cube 2me. Achha, dp you dp you put the value 1 by root 2. Here there will be root m divided by root 2 into e to the power of minus half into de. Okay, so this is 8 means 2 cube divided by 2 to the power half, 1 to the power 6 minus 1, 5 to the power 5 by 2. So this will be, I think, 4 root 2 into 4 root 2 into there will be 1 pi h cube e to the power 1 e to the power 1 minus square root of e. Okay, and there will be m here, so m to the power 3 by 2 into de. Okay, so this will be the thing, 4 root 2 into pi by h cube square root of e into m to the power 3 by 2 by h cube into d. So from here, what do you see? That GE is proportional to e to the power of half. Okay, G is proportional to e to the power of G, yeah, e to the power of half, square root of e. Okay, G is proportional to e to the power of half. So if you plot a graph between density of the in 3 dimensions, this is in 3 dimensions. Okay, if you plot a graph of GE versus E, what graph will you get? So G that is G square E will be some constant, say C into E. So it will be a parabola. Okay, so it will be a parabola. What kind of parabola it will be? It will be like this. This will be G versus E. Okay, so in your assignment I will give you how to draw what will be the relation between G versus E for 2 dimension and 1 dimension. Okay, so in this way this you have to calculate. This is the density of states. GD is what? GD is the total number of phase cells in the energy range E and E plus dt. So GD is what? GD is actually the total number of phase cells, total number of phase cells or microstates, total number of phase cells or microstates in the energy range, E and E plus D, total number of phase cells in the phase cells or microstates in the energy range E and E plus D. So these are actually phase cells and density of states. Okay, now this GE derivation you will need later, this GE derivation. Okay, Achha, now comes your these things, that is classical statistics and quantum statistics. Okay, so I had told you that classical statistics is given by Maxwell Boltzmann statistics. Okay, and quantum statistics are of two types. Quantum statistics are of two types. What are they? Quantum statistics are of two types. One is Bose-Einstein statistics, and another one is Fermi-Dirac statistics. Bose-Einstein statistics and Fermi-Dirac statistics. What are they? Okay. So Maxwell Boltzmann statistics. Maxwell-Boltzmann statistics. Okay. The basic postulates. The basic postulates of Maxwell-Boltzmann statistics are: number one, okay, particles are distinguishable particles. Particles are distinguishable particles. Okay, particles are distinguishable particles. Okay, particles are spinless particles. Okay, particles are spinless particles. Oh, for here actually one thing I forgot to mention here is that here 2 has to be multiplied. Okay, 2 has to be multiplied here. Why this 2 has to be multiplied? Because of the spin. Okay. These are our total number of phase cells. Okay, now each particle can have two spins, that is plus spin and minus spin. Okay, each particle can have two spins, that is plus spin and minus spin. So to accommodate them, you need another one extra cell to accommodate them. That is why you have to multiply it by 2. That is why you have to multiply it by 2. Okay, this 2 to account for the spin. You have to multiply 2 to account for the spin. Okay. Okay, now I mean for classical particles these two will not be there. Okay, I'm writing it here. Wait. So ultimately here I forgot that V here. Here there will be one V also here. Okay, so ultimately what this equation will be? This equation will be 1 by h cube. Okay, 4 pi v. Okay, square root of 2 into e and square root of 2 into e m to the power 3 by 2. Okay, this is the thing, into d. Okay, so this is the thing. Now for particles, that is electrons, for particles having two allowed values, allowed values of ms, that is spin quantum number ms. Okay, the number of quantum states, the number of quantum states is 2 times, number of quantum states is 2 times that of okay, the number of quantum states is twice that of this, say equation number 1 of equation 1 for particles having two allowed values of ms. Okay, see here for this one ms value here, how many states are here? 2 states are here. So because of this ms, 2 states. If this ms was not there, then state would have been 1. But because of this ms, the states are 2. So you definitely you have to account for ms. You have to multiply it by 2. Okay, so this is the thing. Okay, so particles. So now let us come to this Maxwell Boltzmann statistics. Particles are distinguishable. First property: particles are spinless particles. Okay, and most important is that particles does not obey particles does not obey Pauli's exclusion principle. Pauli's exclusion, that is, these are not quantum particles. Pauli's exclusion principle. Okay, particles does not obey Pauli's exclusion principle. What is Pauli's exclusion principle? No two particles having the same set of quantum numbers can be in the same state. Okay, no two particles having same quantum number can be in the same state. This is the Pauli exclusion. Now it does not obey Pauli exclusion. That is, in a particular energy state, any number of particles can be present in a particular energy state. Okay, any number of particles can be present in a particular energy state. So, example of these are what? Example are gas molecules at high temperature, gas molecule at high temperature and low pressure, gas molecules at high temperature and low pressure. Okay, gas molecules at high temperature and low pressure. Now let us uh, let us do that thing. Let us do the arrangement. Okay, suppose there are three energy levels. Okay, suppose there are three energy levels. That is, one is E, 2E, and 3E. You can take the lowest energy level as 0 also, 0E, 2E, like that. And there are two particles. Okay, and there are two particles. I am doing this easiest example. And there are two particles. Now, since particles are distinguishable, let us take the particles as A and B. Okay, so so now particles are distinguishable. You obey this postulate and proceed. Particles are distinguishable. So A and B, you take the particle. Okay. Particles are spinless. So when particles does not obey Pauli exclusion clause. So any number of particles can be in any state. Okay, so here A, B, all the particles are in E. So all the particles here. So this will be 0, 0. Achha, this will be 0, AB, 0. This will be 0, 0, AB. Okay. In this way, particles can be arranged. All the two particles are in the energy level E. No particles, since all the particles are here, no particles are in energy 2E, no particles are in energy 3. All the particles are there are no particles in energy level E. So all the two particles are in energy level 2E and no particles in 3. There are no particles in energy E, no particles in 2E, and all the two particles are in energy level 3. Then A, B, 0. Okay, B, A, 0. A, 0, B. B, 0, A. Then then 0, A, B, 0, B, A. Okay, 0, B, A. Now here you see the total number of I mean, in this case the macro state is what? Macro state is basically 200 is the macro state. You can write it here, macro state, and here micro state. Macro state here is what? 200. Here macro state is what? 0, 2, 0. Here macro state is 0, 0, 2. Okay. Achha, here macro state is what? Here these two have the same macro state. Okay, what is the macro state? 1, 1, 0. This is the macro state. And corresponding to this, the number of microstates are what? Corresponding to this microstate number, there are two microstates. Again, for this one, there are I mean, there the macro state is what? 1, 0, 1, and similarly the number of microstates is 2. And again for this one, the macro state is what? 0, 1, 1, and number of microstates is 2. Okay, so total number of microstates is what? Here the number of microstates is 1, here 1, here 1. So 2 plus 2, 4 plus 2, 6, 6 plus 3, 8. Total number of microstate will be equal to 6 plus 3, 9. Okay, 6 plus 3, 9. Total number of microstates is 2 plus 2, 4, 4 plus 2, 6, 7 plus 1, 8, 8 plus 1, 9. Okay, so here this is Maxwell Boltzmann statistics. Okay, now let's come to the quantum statistics, that is B statistics. Okay, now let us come to the B statistics, that is Bose-Einstein statistics. Bose-Einstein statistics. Okay, now what happens here? Okay, again there are how many energy levels? 3 energy levels, that is E, 2E and 3. Okay, there are 3 energy levels and 2 bodies. Acha. Oh, sorry, I should have told the postulates first. So let me tell here the basic postulates. The basic postulates. Acha. The basic postulates for this. So these are quantum statistics. The basic postulates are particles are indistinguishable. Particles are indistinguishable. Okay. Acha. Particles they are spinless. Now here the particles have integral spin. Particles have integral spin. Okay, that is integral spin means what? 0, plus minus 1, plus minus 2, plus minus 3 like that. But no plus minus half, plus minus 2 like that. Okay. Achha, number 3 is particles does not obey. Particle does not obey Pauli's exclusion principle. Particles does not obey Pauli's exclusion principle.